So working with triangles, another type of math that involves triangles is what's called the Pythagorean theorem. So again, you may be familiar with the Pythagorean theorem. So Pythagorean theorem is a rule in geometry that applies only to right-angled triangles. So it it is specific to what we call a right triangle. So a right triangle is a triangle that has exactly one right angle in it, or one corner, if you will, a 90-degree angle. So the the Pythagorean theorem kind of says if you have a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So if I give you a right triangle, and I usually draw it this way, but that's not bad. So notice how this is considered a corner or a right angle. Now, opposite the right angle is what's called the hypotenuse. So, so as I was saying, we have a right triangle. And again, a right triangle, we have this corner. And the side that's opposite this right angle is called the hypotenuse. And then these two sides that make the right angle are called legs. Now, a lot of times in geometry, we usually just call the legs A and B, and the hypotenuse is usually denoted as C. So what they're saying is the hypotenuse, so instead of spelling this word hypotenuse, we can say, and the square kind of implies exponent. So C to the power 2 kind of implies the square of the hypotenuse, or we call that C squared, is equal to then, is equal to, it's that symbol. The sum means we're going to add the squares of the two other sides, which we would call the legs. So we're going to call this leg here as A. So the square of A, and again, sum means to add, plus the square of B. So in geometry, squaring a side also implies area if you talk about a square. So notice how here's the right angle in our drawing. So 5 would be the hypotenuse. So 5 squared also implies the area of a square. So if I drew out, so if this is a 5 by 5, we know that there's got to be 25 squares inside the square. And if you square this side, in other words, find the area of this side, 3 by 3 is going to give me a 9. And 4, notice how I can make this a square, which means it's 4 by 4, if you will, which makes a 16. So notice that in this example, notice how they also like to write it the other way around. A squared plus B squared is equal to C squared. So notice that 3 squared plus 4 squared does equal 5 squared, because 9 plus 16 does equal 25. So this 3, 4, 5 is a special triangle. It's going to also give us an idea that if you know that one side's 3 and one side's 4, and you have a right triangle, that hypotenuse has to be 5. So this is very powerful in the scheme of memorization. If it's not that, though, then we may have to do a little bit of math. So we can write the formula as a squared plus b squared equals c squared, or we can write the formula as c squared equals a squared plus b squared. Those are two ways of writing it. But notice how if I write it as a squared plus b squared is equal to c squared, you can also solve for a squared by subtracting b squared. So you could say a squared is equal to c squared minus b squared. Or you could have kept the b squared and subtracted the a squared. So you could have said b squared is equal to c squared minus a squared. So notice that you actually can manipulate algebra the same way we did with numbers by just using our property of equality. What you do to one side, do the other, and I can create different formulas. Now, something we have to also know is inverse operations. So we know that when it comes to algebra, if we give you, say, 5 plus 1 is equal to 6, inversely, if I go this direction, 6 minus 1 is going to give me 5. So the inverse of addition is subtraction. Similarly, if I gave you 2 times 5, that don't look like a 5. And we'll use a dot here to keep it a little bit more simple. So 2 times 5, if that equals 10, inversely, I could go the other way and say 10 divided by 5 is equal to 2. So each operation has what we call an inverse operation. So squaring is an operation. So 5 squared is equal to 25. But what must I do to a 25 to get it back to a 5? What's the inverse of squaring? Well, what we've learned is this symbol here is the inverse of squaring. It's called the square root symbol. So the square root of 25 is actually going to take me back to a 5. So we have the square root symbol. So a square root symbol actually undoes squaring. So if I have 5 squared and I have it in a square root symbol, the square root symbol and the power of 2 are inverse operations. They'll cancel each other out, and that'll give you this 5. So that's very powerful to recognize that. Now, you could have wrote this as the square root of 25, but what that's asking is, the question you're asking yourself is what squared gave you 25? If you can answer that question, that's what the square root of 25 is. What squared gives you 25 would be 5. But a quick way of recognizing it is, hey, I got this square symbol and I got this square. Those operations are going to cancel each other out, and you're just left with the 5 because the other two things knock themselves out. So when it gets into the Pythagorean theorem, we start to work with exponents. And remember, an exponent, like we're saying, 3 squared means 3 times 3, which is 9. 4 squared means 4 times 4, which is 16. 5 squared means 5 times 5, which is 25. So an exponent tells you how many times to multiply the base number, if you will. So if I look at this example, it says find the length of the third side. So notice how here's our right angle. This means this is the hypotenuse. And then this must be what we call a leg, and this must be a leg. So remember, the legs are the A's and the B's. So we know that in our formula that the hypotenuse squared is equal to a leg squared plus a leg squared, where I can use this A and B to replace those words. So notice how we don't know what the hypotenuse is, so the hypotenuse squared, but we do know what the leg is. It's 15 squared. And we do know that we have this 36 squared. So 15 squared plus this 36 squared. Now it looks like I'm needing a calculator. So let me pause and see if I can fish out a calculator for you to see on my screen. So let's look at this problem again with a calculator in hand. So we don't know the hypotenuse. Again, I knew this is the hypotenuse because this is the right angle. So the square of the hypotenuse must equal the side squared plus the other side squared. Now in a calculator, if you have a graphing calculator, the square is actually this x to the power of 2. So if I type in 15 and hit this little x to the power of 2, it'll square that for me. That's going to be 225. And then if I do 36 and square that, that'll give me 1296. So c squared is going to equal this 225 plus this 1296. So c squared is going to equal, and I can add these two together. So that 1296, if I add to that, so if I just hit the plus sign, it'll bring down the 1296. And if I add the 225 to that, I should be getting something a little bit over 1500. So 1521. So c squared is going to equal this 1521. Now, to solve for c, we have to take the square root, because remember, the square root will undo the square. So if I take the square root, so if I take the square root of this side, I have to take the square of this side. Now remember, the square of c squared, these are inverse operations. That turns into just a c. So mathematically, all I got to do is take the square root of 1521. Now, my calculator, the square root is actually above x squared, so it's in blue. Anything in blue, though, we have to hit this little button up here, the second button. So if I hit the second button, I can take the square root of 1521. Now, again, you don't have to have this calculator, but if you do have this calculator, you can type it in that way. So if your calculator works differently, feel free to use it as you need to. So notice how C would be 39. So that was going to be then 39 feet, if you will. So notice that this side's 36. And remember, the hypotenuse has got to be the longest side. It's got to be bigger than 36. Did we get something bigger than 36? Yeah. So that sounds reasonable. So always look at your answers and see if they make sense. And again, you could type in 39 squared and see if it actually equals 1521. So if you type in 39 squared, it should equal 1521, and it does. Because c squared must equal this 1521. That's the Pythagorean theorem. So if I look at this problem here, it says find the length of the third side of the right triangle, give an exact answer and an approximation to 3 decimal places if needed. So if it's not an exact answer, we may have to round to 3 decimal places. So let's see what we got here. So notice how, again, we do have a right triangle. That means this is the hypotenuse, and these are the legs. Now, since we don't know the legs, I'm going to flip my equation around and say, hey, a squared plus b squared is equal to c squared. Since we're looking for one of the legs, I like to have that on the left side because I'm more of a left or right person. We don't know what a squared is, but we do know that the b is 36. That's 36 squared, and that must equal this 39 squared. But if memory serves me though, this is 36 here. This was 39. I'm thinking, excuse me, based on my previous problem, my leg should be 15. So if we play this math out, let's see if we actually get 15, because it looks like the same math, just different thing. So a squared is going to equal, or plus this 36 squared. Well, we did this 36 squared earlier, and we got 1296 equals 39 squared. Well, I just did that 39 squared. We didn't have to throw that math away. So 1521. So to find a squared, we'd have to subtract 1296 on both sides. So I have to go 1521 minus 1296. And I do get 225. Now remember, to solve for A, you still got one more move to do. To get rid of this power 2, you have to use the square root symbol because it undoes squaring. And you have to also do that to the other side. By doing so, I'm left with A. So I end up with this A here. And the square root of 225 would be what A is. So second x squared gives me my square root symbol, 225, and that does give me 15. So in this example, it's almost the exact same problem. They just gave us different information. So you can always use previous information to solve a problem. This Pythagorean theorem would not be required because of the previous information that we've done. Okay, so I'll stop there. But briefly, though, if I do want to take the square root and it's not clean, So suppose I have like 220. Let me try to do this again. The square root of 220. That don't look right here. The square root of 220. Now, if it did say round to three decimal places, what that means is you actually have to go three places past the decimal. So what I'm looking at is this 2. What I have to do is to decide whether to keep the 2 or round it up to a 3. What tells me how to do that is the number next to it. Since there's a 3 in this fourth place, this 3 would say round back down to the 2 as opposed to rounding up to a 3. So if we had to do the square root of 220, notice that the answer would have been like 14.832 because the 3 would say keep the 2. Now, if that was a 5 or more, then that would have been 14.833. So that's just a little sidebar information there on that.